This video demonstrates the use of transfer capacity analysis, one of the functions available in the Transmission Network Tools toolbox. Study case 05 Transmission Network Tools TCA should be active. Transfer capacity analysis is used to determine the maximum feasible power flow between two parts of a network by scaling demand or generation in opposite directions in the two parts. Load flow calculations are executed at each step until the critical point is reached. Let's first run a load flow to see the initial state of the network. In this example, we'll consider the transfer between the southeast and the rest of the system. A boundary called NESE interconnector branch has been set up in order to monitor the flows between these two parts of the network. Looking at the results in the overview diagram, we can see that there is a transfer of about 71 megawatts across this boundary. Opening the Layers Configuration dialog, we can use this option to see the direction of active power flow more easily. We see that power is being exported from the southeast. In the Transmission Network Tools toolbox, this icon can be used to set up the transfer capacity analysis. The two parts of the network can be defined either by specifying regions or by specifying sets of elements. We'll use the first option. Two regions are selected. One is the exporting region and one is the importing region. These can be defined by grids, zones, areas, or boundaries. Our exporting region is defined by the interior of the NESE interconnector branch boundary. And as the importing region will be the rest of the network, this boundary has been copied and reversed, and we use the second boundary to define the importing region. Notice how the two interconnecting lines are automatically identified. The analysis can be carried out by scaling generation or demand, or both. In this case, we'll scale the generation. Now, let's look at the constraints page, where the constraining limits are defined. The option to consider thermal constraints is selected, meaning that the thermal ratings of branches will act as limiting factors. In addition, the active power limits of generators will be observed. There are also options to save the output of the analysis, but in this example we will not do this. The analysis is executed, and we can see in the output window that the total transfer from the southeast to the rest of the network has a limit of about 936 megawatts. No thermal ratings have been exceeded. The transfer limit has been found when no more generation can be scaled down in the rest of the network. In reality, the transfer capacity across a boundary may be limited by the impact of potential faults on the network. Returning to the Transfer Capacity Analysis dialog, we can see that there is an option to consider contingencies. If this is selected, the Contingency Analysis Command dialog can be accessed here. In this case, all the single circuit line faults have already been selected. Before executing the analysis, there is a further consideration. It's likely that elements overloaded due to faults will be able to exceed their thermal rating for a limited time, provided that post-fault actions to reduce the overload are available. For this reason, we will increase the maximum thermal loading of the components to 150%. The analysis is executed. This report shows the contingency analysis results for the last feasible solution. We can see that the limiting contingency is a fault on line SEL1. And looking at the output window, we can see that the maximum transfer is now about 756 megawatts.